Hi, everyone. Before I start today, we're just going to do a couple of questions on rotational motion. But before I start, I just want to say something about the rest of the course. We're coming towards the end of the course, and uh, next week, we have Thanksgiving, and so there's only Monday and Tuesday. I don't have any new material. We're actually done with the material. That the rotational motion is our last topic. I could do a live stream on Monday, but I don't see a real need for that because the week after that is going to be the week leading up to the final test, and we'll spend that week reviewing. So I don't think there's a need. Nonetheless, I will be available. I'm going to be around all day. And maybe I'll just send out an email and say, look, does anyone need any help with anything? And if you do, then we could either I could either do a live stream. These are very quick to set up, or I could just do a Google Hangout one-on-one, or just a couple of people at once. But I will be around if you need help. The assignment, rather than making it due today, which is the usual, I made it due the Tuesday before. We break for Thanksgiving. That's your last assignment of the year for the semester, and so there's just the test after that. Okay, so just to be very clear, I will produce a very short video next week. And it's not about this semester, it's about next semester. A couple of changes I'm going to make. Okay, I'm just going to propose them to people, and for feedback, because this is a very unusual situation to be teaching in, and I just want to make sure that people are like, if you have suggestions, because you've taken other courses with other professors, and maybe you say, I like what they did, I don't like what you did, or whatever. And I mean, now's the opportunity to change things, because once things are set in the syllabus and people start making decisions based on that, it's not something that I could easily change, because then you got to like be fair to everyone. It's just much better to get it right up front. So anyhow, that's it. Okay. So today we're just going to do a couple of questions. These were actually questions that I had on the assignment originally in one form or another, but the assignment got very long. Okay, I don't remember how many questions, but as I started to realize it was getting too long, I said, you know what, let me take out these two questions and we'll do them together. They're the two most subtle points that at least I see as subtle points in rotational motion. And so I thought, you know what, let's just do them together, and be able to work through some of the subtleties. Okay, so the first one is actually a classic problem in this in rotational motion. And if you just go on YouTube or any video site and just look for physics experiment rolling soup cans down an inclined plane, you're going to see a lot of these examples. Basically, they have soup cans, and like one soup can might be something like cream of mushroom soup, and another one might be like chicken broth, and they roll, and when they roll, one gets down to the bottom before the other, and you wonder why is that happening. Okay, now I did do that and talked about that in the pre-recorded lecture, but I'm going to make a variation on that here, and it's going to, I wouldn't say bring out a subtlety, but it'll bring out another variation on that problem. Okay, so well, let's start. That's the first problem. Okay, so we have a large cylindrical soup can with a mass of 750 grams. I have large cans of soup, and they're pretty big. They're getting like a pound and a half, so 750 grams, and a radius of 5 centimeters. Okay, so it's cylindrical, and 750 gram weight, and radius of 5 centimeters, and it rolls downhill without slipping, dropping a vertical height of 75 centimeters. Okay, so this is a conservation of energy. The details of how it goes downhill don't matter. It's just that it drops vertically 75 centimeters, and that's all you need to know. Okay, and then there's a series of questions. So the first question I ask is, assuming the mass is uniform. Now this is actually kind of important, because if you look at how I uh, presented the calculation of the moment of inertia, first I did point masses. Okay, and each point mass has a contribution mr squared to the total moment of inertia. But then I said I gave you some formulas for particular shapes. Okay, and things like spheres and disks and so on. And in all of those, the assumption is that the mass is uniform. If the mass is not uniform, those formulas don't work. Okay, so here I have a cylindrical soup can, and I'm going to say, let's assume that the mass is uniform. What's the moment of inertia? In this case, you can use this formula right here. Okay, 1/2 mr squared, where m is the mass and r is the radius of the cylinder. Okay, not the height of the cylinder. All right. Now, you might say, well, where did you get that formula? That's actually the formula for a disk. And the reason it doesn't matter whether you're talking a disk or a cylinder is because a disk is just a very, very thin cylinder. Or not a thin cylinder, but a cylinder with very little height. Okay. The height of the cylinder doesn't matter Okay, so it's only the radius, it's only the radial distribution of the mass that makes a difference with the moment of inertia. So the formula for the moment of inertia of a disk, for a cylinder, it's the same. Okay, it's 1/2 mr squared. Well, the rest is trivial. There's the half. The mass is 750 grams, but converted to kilograms is 0.75. The radius is, where's the radius here? 5 centimeters. Okay, so that's 0.05 meters squared. Now that's going to give a very small number because 0.05 is small, but then you're squaring, it gets even smaller, and so you get a really small number for the moment of inertia. And this is not atypical. Okay, and so I wrote it in scientific notation here. Um, 9.375 times 10 to the minus 4 kilogram meters squared, and the units are kilogram meters squared. Okay, so there you go. There's the answer to the first one. And again, that's assuming that everything is uniform. Okay, which is approximately true for something like cream of mushroom soup. I know that the metal at the edges is more than the has more mass than the greater density than the soup, but roughly speaking, it's uniform. Okay, so what's the next question? So now I say, well, how fast is it moving when it rolls to the bottom of the hill? And if you again go back to the my notes or the pre-recorded lecture, what you'll see there is that I have a formula for this. I looked at a drum rolling downhill, and then I also did a ball, like a sphere, rolling downhill. And for each one of them, we got slightly different formulas. Okay, and there's no reason why you can't use those formulas. All right, it was an open book test. So if I give you something like that, and it's a drum rolling downhill, just use the formula because there's no need to rederive it. Okay, and so if you go back to that to those notes, you will see that the formula for the velocity when it gets to the bottom of the hill, that's what, by the way, that's why I did derive that without using any numbers, because if I'd used numbers, then you wouldn't get a formula out at the end and you'd have to redo all the steps. But here, with a just using the symbols in there, the variables, you get actually a formula. And the velocity at the bottom depends on, of course, g, the acceleration due to gravity, okay, but also the vertical height, and that's it. It doesn't depend on anything else, okay. But there's this 4/3 in there, so square root of 4/3 g over h. That 4/3, you go, well, where did that come from? That actually came from, if you go back to the derivation, it actually came from the formula for I. Okay, so because I has a particular structure to it, all of the formulas for I, and I only gave you a couple. I did, like, what did I do? I did the drum or disc. I did a solid sphere, and I did a rod with the axis of rotation either at the end point or at the middle. But there's lots of them. Lots of these formulas. Okay, they all have roughly the same form, mr squared, with some factor out in front. This 4/3 that you're getting here, that came from that factor of a half out front there, like that. Okay, so without going through the details, that's where it came from. Okay, so this is the formula for the velocity when a drum rolls to the bottom of the hill, provided that the cylinder or drum is of uniform mass. Okay, so now it's just a matter of plugging in the numbers. 4/3, okay, and g, well, 9.8, but we've been rounding off to 10, and then h is 0.75, okay, and that gives us a velocity of 3.16 meters per second. All right, so there you go. That's how fast this can of soup would be going when it rolls downhill, dropping a vertical height of 75 centimeters. Okay, now so far this is nothing new over what I did in the lecture. Here I say, let's now assume that the drum is not uniform. The can of soup is not uniform. And, there could be lots of reasons for this. We don't have to worry about the details. And I give you I, okay? I tell you that I is equal to 5 times 10 to the minus 4 kilogram meters squared, okay? So this is just a little bit more than half of what it was above, okay? And then I ask, of course, how fast is it going when it gets to the bottom of the hill? Now, this time, you really can't use just some formula for V. Okay, there's no way of deriving that because there's no formula for a general value of I. You have to redo the entire analysis in terms of conservation of energy. Okay, so that's what I'm going to do right now. All right, so When the drum rolls downhill, rolling or any kind of a wheel, this is what makes wheels so important. A wheel, there is friction, but because the wheel, when it touches the ground, it's not slipping across the ground, it's that slipping of one surface across another. That's the friction that causes heat. So, when this rolls downhill, there might be friction there. In fact, there has to be friction there, otherwise it wouldn't roll. Okay, but the friction isn't causing the energy to be dissipated as heat, and that's another way to think about the beauty of a wheel. That's why the wheel was such an important invention, because at that point where the wheel touches the ground, that point there, it isn't slipping. Okay, it's actually just touching, and so if you don't have slippage, you don't have friction, and uh, you don't have kinetic friction, you don't have energy dissipated away. And in fact, even though the wheel is moving, your car is moving, where the wheel touches the ground, that's static friction. Okay, if you think about it, it's rather remarkable. But anyhow, a bit of a digression. Okay, but it's important because energy is not being dissipated away here. Okay, so when the drum is at the top of the hill, it's all potential energy. Now, I didn't say it starts from rest. I mean, on a test, I'd be very careful, but we're doing this together. So just assume that, when this is a can of soup is at the top, I'm just going to release it from rest. Okay. So it's got no kinetic energy. It's all potential energy and gravitational potential energy. There's no spring here. So it's mgh. Okay. And so if you plug in the values here, mgh, you get 0.75 times 10 times 0.75. This first 0.75 is the 750 grams, and this 0.75 is the 75 centimeters for H. Okay, and that works out to an energy of 5.625 joules. Okay, so all through this motion, as the can of soup rolls downhill, the energy is the same. All right, so it's the same because it's conserved. All right, now when it gets to the bottom, so I call that E primed, the energy, it's still the same value, but just said E prime to emphasize that this is after it rolled downhill. The energy now is all kinetic, but up until before rotational motion, we only knew about kinetic energy because of translation. So if something is moving, like just like moving in physics, we call translation when it moves from one position to another. Okay, so because the all we knew about was translational kinetic energy, we just had that kinetic energy was equal to 1/2 mv squared. Okay, but now we know that there's also a kinetic energy associated with something rotating. Okay, so even if the object is in place, in other words, it's not translating, it's just sitting in place and rotating, it has kinetic energy. All right. Now, some of you are chemistry majors or even biology majors, and you might say, well, how does this relate to my field? Well, down at the microscopic level, things like the oxygen molecule are little dumbbells, okay? And the oxygen molecule doesn't just have energy in a gas because it's moving; it's also got energy because it's rotating, okay? So this works all the way down to the microscopics, okay? So this part here, that's the translational kinetic energy, and there is the rotational kinetic energy. Okay, and the energy, this 5.625 joules, gets distributed between a little bit goes into translation, a little bit goes into rotation. The more that gets siphoned away into rotation, the less is available for translation, and if there's less available for translation, the slower it's moving. Okay, so that's kind of the intuition you should have behind this. The only other thing you need here is the condition for rolling without slipping. Okay, so I just said rolling there, but I really should say rolling without slipping, and that is that the angular velocity of the object is equal to the velocity of the center of mass, that's v, divided by the radius of the object. Okay, so that omega is like how fast it's rotating around the center of mass. The v there is how fast the center of mass is moving, and r is the radius of the object. Okay, so we don't have a formula for I because it's not uniform. Like, how would you do it? But I gave you I. Okay, and so if we now substitute into this for E, well, energy is conserved, so we still have that 5.625. Okay, 1/2 mv squared. So there's the half. There's the m, 0.75. V we don't know. That's what we're solving for. Okay, so leave that alone. All right, and then there's the half right there. I give you, it's 5 times 10 to the minus 4. And the omega, you don't have a value of omega, but you have, you could write it in terms of V over R. Okay, so this whole thing here is omega, written as V over R, so that there's the V. And for the R, I do tell you that the R is 5 centimeters or 0.05 meters, okay? And so just reducing this, I mean, the rest is just some arithmetic. Just reducing this part right here is that number there. 0.05 squared, yeah, well, there it is there. I didn't square it out, but then I can reduce it a little bit more. That divided by that turns out to be 0.1. And so here you go. Here's the energy. Here's the energy in translational kinetic energy, and there's the remainder that goes into rotational kinetic energy. And working that out, it turns out that the velocity is now 3.44 meters per second. Why is it different? Before, we had 3.16, and now we have more, 3.44. Well, what happened is that the smaller I is, the smaller the moment of inertia is, right here, the smaller that I is, the less energy gets siphoned away as rotational, and there's more energy available for translation, and that's why it's moving faster. Okay, so remember, translation just means, the motion of its center of mass, okay, through space. Okay, and so less energy is getting siphoned away as rotational kinetic energy, the more is available for translational kinetic energy, and the faster it's going to be moving. All right, so that's how you do that one. So I think you could see how that's different, because like if you have a formula for I in terms of like M and R, then you have a formula for V in terms of just H. Okay, but if you don't have a formula for I like that, well, then you just have to redo the entire energy analysis there. Okay, and then you can still get out the velocity at the end. By the way, another thing I could have asked for next, okay, I didn't do it here, is for omega, because once you've got V, okay, right here, once you've got V, and of course you have R, then you can also have omega. So at the bottom of the hill, not only can you say how fast is it moving, how fast is the center of mass moving, but you can also say how fast it's spinning. Okay, so that's easy enough. I don't think it's that necessary to do that problem. Okay, let me see if there's any questions in the chat before I go on. All right, I'm seeing four users right now on connected. Okay, well, let's continue. The YouTube interface has been weird, and it's just not just me. Other people have been saying the same thing. It doesn't always show how many people are actually watching your live streams, but that's all right. I mean, I'm sure that there are some people watching. Okay, so the last question is: assume that the can slides downhill without rotating at all, without rolling at all. Okay, so in other words, like, maybe it's a very slippery surface and you just put the can there and it doesn't even rotate, it just like slides downhill like that. Okay, like a block would. All right, now how fast is it going at the bottom? So I did this just like I did in the pre-recorded lecture, just to show you the difference when there's no rotation at all. Well, if there's no rotation at all, there's no energy going into rotational kinetic energy. It's all translational, and you're going to get an even bigger V. Okay, so here we go. The energy afterwards, it's all translation. It's all 1/2 mv squared, and so that the total energy is still 5.625. That's going to equal the 1/2 m is that 0.375 v squared. Solving for v, you get 3.87 meters per second. Okay, and so you could see that as the uh, um, rotational kinetic energy gets smaller, the velocity gets bigger. All right, so that's it for that problem. I thought it was a little bit subtle, just because you have to switch tactics, even though you're answering the same question. One is how fast, both parts B and C, you're saying how fast is it moving downhill. But in one of them, because you made this assumption of the uniformity and you had a formula for I, we actually have a formula for V. But if you don't know, if you just have like this number for I, maybe you experimentally measured it or whatever, there's no way avoiding doing the full analysis of the energy. Okay, so there's that problem. All right, let's do the next problem. So the next problem is a problem where it's an angular momentum problem, but it's an angular momentum problem where you're kind of bringing together linear momentum and angular momentum. Okay, and I think you've seen now, especially if you've done the assignment and worked through it, that there's a relationship between angular quantities and linear quantities. They're not independent of one another. And the relationship, it's actually right here. It's this relationship right here, the rolling relationship right there. Okay. Basically, if you have your linear quantity and you divide by r, the radius of whatever is rotating, you get the angular quantity. Or conversely, if you have the angular quantity and you multiply by r, you get the linear quantity. Okay, and same is true for angular momentum. Okay, and so it's sometimes it's a little hard to picture the situation where you have something which seems like purely linear momentum, and then afterwards is purely angular momentum. You go, well, how did the two glue together? And this was the very last problem I did in the lecture. And like I had that rod there that was like sort of free to rotate about an axis up here. So an axis up here at the top of, say, my remote here, an axis right up here. So this thing is free to rotate around that. And then I had this bullet coming in, and it would embed inside the piece of wood, and it would cause this thing to rotate. Okay, so there, when the bullet is just moving before it embeds itself, it's linear momentum. And then, of course, once it's embedded and the whole thing is spinning, it's angular momentum. I just thought we'd do that again, but in a slightly different context. So I have a problem here with a merry-go-round, and it's made up of a circular disc of mass 75 kilograms and radius 1.5 meter. The merry-go-round is initially at rest. A child of mass 50 kilograms, is about 100 pound, okay, runs at 6 meters per second and jumps onto the edge of this merry-go-round, grabs hold, and then, of course, the child and the merry-go-round are going to be spinning afterwards. So the first question is, how fast are they spinning? That's a bit ambiguous. Really, I want the angular velocity there. So again, on a test, I'd probably say angular velocity. But then I also ask, what's the tangential velocity? And then the last question is, how much energy is lost in this collision? Okay, so in physics, a collision is any time when two objects interact. All right, it's very broad meaning of a collision. All right. So, these two, the child and the merry-go-round, they're kind of grabbing on together. So it's a collision in which the things stick together. And whenever you get a collision where things stick together, the energy is always less afterwards. In other words, an inelastic collision. Okay, and I'm just going to show you a picture of a merry-go-round because usually when you picture merry-go-rounds, is you think of like a carnival with like the little horses that bob up and down. But I remember when I was a kid, we had these kinds of merry-go-rounds right here. Okay, and they were like these metal discs, and you just grab them and you make them rotate. And I don't see them anymore in playgrounds, but I can't help but wonder if maybe they've gotten rid of them because they're a bit dangerous. I remember doing some pretty crazy things as a kid, probably things that were not smart, and so I don't know. But they're also called merry-go-rounds or carousels. Okay, so uh, that's what this child is running up to and grabbing onto the end. Okay, so actually, let me go back to this and let me show you another uh, image here. Okay, and in this image, what we're doing is we're actually looking down on the merry-go-round, and let me put a little dot in the middle here like that. So that's the center right there. Okay, and the blue line indicates the child running up to the merry-go-round and then jumping on. The black dot there is the child jumping on. And so you could see that, up until the child jumps onto this thing, they're moving along a straight line, and so it's a linear momentum. But then after the child jumps on, the child and the merry-go-round will go around in a circle like that, and then you have rotational motion. Okay, and you say, well, how do I do this problem? Well, the trick is this moment right here, okay, when the child jumps on, because that's the transitional point between the linear and the angular. Okay, the radius at this point here, that radius right there, so you can see like the blue vector is the velocity and the red vector is like r. That radius there, what did I say it was? 1.5 meters. Yeah, okay, so it's like 1.5 meters, like that. Okay, and the velocity, I guess I'll do that in blue, is the velocity as the child moves is 6 meters per second, like this. All right. And even when the child is like just before the child grabs on, this system has a linear momentum. And linear momentum is usually given, actually it's usually given the symbol scripted L, okay? Although now in my other whiteboard I can't do a scripted L. And that's just going to equal I times omega, where I is the moment of inertia and omega is the angular velocity, okay? Now, if you have more than one object, then of course you would just add in, another I omega and then another I omega, one for each of the objects, okay? But, both before and after, you can think of the before it's just the child, after it's the child plus the merry-go-round, but you could still think of it as one object, okay? So what we have to answer for the angular momentum before, that is before the child grabs onto the merry-go-round, child is there, but it's just like an instant before, okay? It's like, what's the moment of inertia of the child? And you go, well, I don't know, because like there's no rotational motion. But you can treat at that moment there the child as a point mass. And the moment of inertia of a point mass is mr squared. Okay. Now, when I had the dumbbell or the multiple masses, I mean, I would have had mr squared for one plus mr squared for another and so on. But now we just have one mass, the child, and so it's just mr squared like that. Okay, and that's the moment of inertia of the child, right at this point right there. Okay, and so m, of course, is, what did I say, 50 kilograms, and r is 1.5 meters, and so that gives you the squared, of course, and that gives you I for the that goes into here. Okay, that gives you that I that goes into there. Okay, we'll finish it off on the other whiteboard. Okay, but we also have to look at omega, and omega, what's that going to equal? Well, how do you get it out of the linear velocity? Because there's a relationship between the linear velocity and the angular velocity, and at that point, it's v divided by r, like that. And of course, v is 6, and r is 1.5, and that gives you actually 4. Okay, like that. So it's really at this point right there, when, just before the child jumps on, or in the example that I did in my lecture, just before the bullet embeds itself, that's the point where there's a transition between linear and angular, and you can glue the two together. And you can see here that, basically, I got the moment of inertia of the child, and I also got the angular velocity of the child at that point. All right. So let's finish that off on the other whiteboard. Okay. So here's the angular momentum. And that's conserved, so that's why we want to calculate that. The moment of inertia of the child, that's mr squared. So substituting in the numbers, 50 times 1.5 squared gives me a moment of inertia of the child of 112.5 kilogram meters squared. Okay, and there's no condensed values for um, like there's no equivalent of an abbreviation of kilogram meters squared. That's it for the units, MKS units for moment of inertia. Okay, and then for the angular velocity, it's v over r. That's 1.6 divided by 1.5, or 4 radians per second. Okay, so substituting that into L is equal to I omega, you get those values from above, and that turns out to be 450 kilogram meters squared per second. Okay, and you might wonder what happened to radians. Remember, radians are not really a unit, because radians are just a ratio of two lengths, and if you got like meters divided by meters, the meters cancel out, giving you a dimensionless quantity. Okay, and so the radians, I just dropped it out of there. Okay, so those are the units for angular momentum in the units for angular momentum in MKS, so kilogram meters squared per second. All right, that quantity is conserved throughout the dynamics. All right, so afterwards you have the same formula, but now I put the little dashes there to indicate that it's after the interaction, after the child is grabbed on and the child is spinning. Okay, so this moment of inertia here, is not just the moment of inertia of the child, it's the moment of inertia of the child plus the merry-go-round, because both of them are spinning together. Okay, and we have the moment of inertia of the child, that's what we just calculated, that was that 112.5. We need the moment of inertia of the merry-go-round, okay, and it's a disk, so just like in the previous problem, 1/2 mr squared, okay, and just substituting in the numbers. M for the merry-go-round, I said, was 75 kilograms, radius was 1.5, so that gives us a moment of inertia for the merry-go-round of 84.375. Okay, the total is going to be the sum of the two, the moment of inertia of the child in the merry-go-round, and that's 112.5 plus the 84.375, which gives us 196.875, rounds off to 197. Okay, so what's that give us? Well, we don't know omega, okay, but that's what we're trying to find. We're trying to find how fast is this thing spinning afterwards. L primed, the angular momentum after the interaction, is the same as before. That's 450. Okay, I we have, and that gives us an omega of 2.29 radians per second. Okay, so that's how fast the child and merry-go-round are spinning. Okay, 2.29 radians per second. All right, so not a very intuitive number. I mean, it might be better if we translated it into revolutions per minute. I didn't ask you to do that, but that would be a bit more intuitive number. Okay, but I did ask for the tangential velocity, and the tangential velocity, that's basically, again, you've got the angular and you want to get the linear, and the linear quantity is related to the angular quantity by multiplying by r. Okay, so tangential velocity is equal to r times the angular velocity. The radius there is 1.5 because the child is at a distance of 1.5 meters from the center of the merry-go-round, multiplied by the angular velocity that we just calculated, and that gives us a velocity of 3.43 meters per second. Okay, so at this point you should ask yourself, does it make sense? See, it's a little hard to see if this number makes sense because you don't have a good intuition into like what a radian per second is. Okay, but this number, we can compare it to something because the child, when they're running up to the merry-go-round, are running at 6 meters per second. So when they run up and grab, jump on and grab hold, you expect the whole thing to, the child to be slow down because, during the interaction, the child has sped up the merry-go-round a little bit, and so the child themselves must have slowed down until the two reach the same velocity. That's what happens during a collision in which momentum is conserved. Okay, and starts off at 6 meters per second, slows down to 3.43 meters per second, so that makes sense. It wouldn't make any sense if, say, you got 10 there. I mean, could you imagine the child is running at 6 and then grabs on and it actually speeds up to, sorry, my phone is ringing here. One of the dangers of live streams. Okay, so it doesn't make sense if the child were to grab on and it's somehow going faster afterwards than before. Okay, so well, there it is. Okay, and then the last question was how much energy is lost during the interaction. So before the child grabs on, it's all translational kinetic energy. The merry-go-round isn't turning. The child's just moving along a straight line, okay, at some velocity. And so it's just 1/2 mv squared, okay? So there's the half. Child's mass is 50, and v squared is 6 squared, and that gives you 900 joules, okay? So the child has 900 joules of energy running up to this merry-go-round. Once the child grabs on, it's both the child and the merry-go-round that are spinning, okay? And the middle of the merry-go-round, the center of it, it's not translating, so you could just treat that as all just rotational kinetic energy, okay? Because the whole system, it's not like the merry-go-round is going anywhere. It's just spinning in place, okay? And so there's no translational kinetic energy. Now it's all rotational kinetic energy, okay? And so you got 1/2 I, it's the I of the whole system, moment of inertia of both the child and carousel, but we've got that number, and the angular momentum of both of them. Sorry, angular velocity of both of them, okay? And so just plugging in the numbers, you get that the energy afterwards is 514 and some decimals there, okay? Joules. And you could see that the energy after is less than the energy before, and it turns out that it's something like 385.7 joules of energy were lost in this interaction, which is what you expect in an elastic collision. Okay, so well, there's the second problem. All right, so let me just see here if there's any questions in the chat. It looks like there are no questions. If that's the case, that's it right now. Now I could have done some more problems, but I think since we're going to be reviewing these things just before the test, we'll do that. I just wanted to go through these because they were more subtle. I want to end this lecture with live stream, whatever, with just someone asked me how exactly you're going to calculate the final your final grade. Okay, so that's it for the problems. The next thing I'm going to do is how do I calculate the final grade? Well. Uh, uh, to answer that question, always look at the syllabus. The professor in any class, should tell you how you're being graded in that class. So one of the major reasons why you have a syllabus, okay? And so I just gave you here a little bit of an explanation, but this is not, in any way different than what's on the syllabus, okay? So the course is made up of 3 tests, and each test is worth a quarter of your grade, so 25% for all of them. Then we have the assignments, and I made them a quarter of your grade as well. Okay, and so I don't remember the test 2 what it was out of. It doesn't really matter, but like test 1, I think for physics, these are just made up numbers, okay? So I think for Physics 101, your first test was out of 27. So suppose you got 25 out of 27. That would have been 92.6% for your first test, okay? Whoops, that should be a 6 there, not a 3, okay? And so what you would do is you would just take that, 92.6%, write it as a decimal, and then multiply it by 25, okay? And then test 2, I don't know what that would work out to, but let's assume that on test 2 you got 85%, write that as 0.85 multiplied by 25, okay? And then test 3, we haven't done it yet, but I don't know, just assume that you got like 95% on test 3. Well, then write that as 0.95 and then multiply by 25. Okay, and then of course the assignments, you got some grade on the assignments. Suppose it's 92.5, multiply that by 25, add up all those, and you'll get your final answer. So, that's what I did here. So, then in the grade in your course would be like 91.3. And, for the registrar, I got to convert that into a letter grade. And so, that's an A, but it's in the lower 3% bracket, and so that would be an A minus. Okay, the only other thing I got to tell you is how do I actually calculate your assignment grade, because it's made up of a lot of little grades, and that's easy. I just like suppose again, these are just made up because I don't remember the assignment what they were out of, but like here in my example here, I just have 3 assignments. Suppose you got 8 out of 8 on the first assignment, 12 out of 14 on the second one, and 17 out of 18 on the last one. Well, then what were your total points? Well, 8 plus 12 plus 17. So you would have 8 plus 12 plus 17. And then what was it out of? Well, the total was out of 8 plus 14 plus 18, 8 plus 14 plus 18, okay? And in my example here, it turns out to be 92.5, okay? And so that's how I would calculate your final grade. On Canvas, I didn't really set up Canvas to do the weighting right. I'm pretty sure I could figure it out, okay? I just didn't bother to even try, okay? So don't look at your Canvas grade or the way Canvas calculates it, because that's not the way it's calculated. It's always by how the syllabus does it, okay? So I hope that explains it, all right? I know it looks like there's only 3 people viewing, but there it is. There's the explanation. If there's any questions about anything, whether how I graded or or anything else I've said today, just ask. Otherwise, we're done. It's a little bit of a shorter class, but we're coming to the end of the course anyhow. We're pretty much just finishing up right now with stuff. So, any questions with anything, or are we good? Let me actually ask that in the chat as well. Oops. Is everyone okay? Any questions? Or can we end the stream? Question mark. I'm not getting any response. So, all right then. You know what? I'll end the stream, and if you have any questions, of course you can always ask during the Google Hangouts. Okay. So, bye bye everyone.